Hello guys, how are you doing today? We hope everything is fine. Welcome to our third part of our video, Design of 5-Story Building using Response Spectrum Analysis. With the use of staad and RCDC software, in the previous video, which was part 2, we easily, smoothly designed the concrete beams, columns, and shear wall. In this video, suppose we use this slightly edited model where there are members of this structure fail in the design calculation. We will try to diagnose the type of failure and try to sort them out to design members in accordance with the relevant code. Let us use this file where I encountered some beam failures during the software analysis, and I'll show you what I did to achieve this design. Now let us open this file. According to the code, if we use response spectrum analysis in designing a regular structure, we need to know B shears of this structure calculated both by equivalent lateral force procedure and response spectrum analysis, just like we did in previous video. So if it happens you haven't yet watched the video, please click the link below in the video description box. Now let us open the file to qualify ourselves of following the code by checking the B shear. In the left side version, let us double click this floor diagram. Then scroll down a little bit as shown here. We can find here what we are looking for. Record here the value of Bx is equal to 1771.17 kN. This is along X direction. And in Z direction, let us scroll down a little bit further. Record this, we have Bg is equal to 2014.33 kN. For response spectrum, let us double click this participation factor here. Jot this down. The value Bx is equal to 1029.02 kN. This is along X direction. And for Z direction, Bg is equal to 1163.62 kN. Note that our V shear Vx and Bg in response spectrum is less than the value of that obtained in ALF procedure. So we have to do the scaling. As we know, response spectrum analysis is an iterative process, so that every change in model, especially change in its member size, we have to repeat also this process of B shear scaling. Alongside with this, it is important to check the participation factors if they are consistently within the minimum requirement. And if they aren't, we have to add number of modes until we meet the requirement. And we found out here that there is no problem with the participation factors. However, the B shear values do not conform to our code specification. What we gonna do here, let us exit this viewer and go back to workflow page control panel and click loading. Expand this load cases details and in the response primary load case here, highlight this and click edit. Since this B shear is less than 1771.17 kN, then let us multiply this 1029.02 kN by a factor X that would make it equal to 1771.17 kN. Solving X is equal to 1.721, and this 1.721 shall be multiplied by the directional factor here. And the product shall be the new value to be entered here. So 1.721 times 0.118 is equal to 0.203. Enter this value here, then click modify. Now let us do the same procedure to Z direction. Highlight this and click edit. So the factor X for Z direction is 1.7316. and multiply this to G directional factor, which is 0.118 is equal to 0.204. Then click modify, then close. Then finally, run analysis. Then after the analysis, close this file. Now to start with, let us open the RCDC software. Now we go to beam first, then we start at 4 meter level. Then click create project. Let's go to settings, then general reinforcement, then click ductile design. Then basic load cases. Then design. Also, we have filled beams group J3 and J12. So, here is our floor framing layout. It is important to check always in here the continuity of beams before digging deeper by just clicking and highlighting beams in every grid line here like this. Grid line by grid line, analyzing if there is something different. By doing this, it would be quite easier to find errors, or else everything would be in miss. As I mentioned in the previous video, for the sake of those who have not yet watched that, if we click these beams and all of the beams in the grid line are highlighted at once, you will think of few things then. The beams belong to one group, and since they are in the same group, they have same dimension, and they are designed considering the ductility property of a reinforced concrete. They act together to resist lateral force and the stresses that are distributed to these beams, so that if one of them fails in this group, all of them in this grid line will be classified as failed beams in the design output. The good thing is, once failed, it is easy to rectify. Just increase beam size and then everything will be fine. Another good thing in this method is, it would be easier to read and interpret the layout of steel reinforcement prepared by the software. However, if we highlight a beam, like this for instance, if we highlight this beam, other beams in this grid line are not highlighted. It means that they are not in the same group. So we'll wonder why these beams are not in the same group. While in the left side, it is visible that they have uniform size, 350 by 500 mm. But they are not grouped together. One thing we must take care of these beams here is the continuity of the reinforcements. Let us check the reinforcement in this particular grid line. The group name is J2, right here. Go to reports, then elevation and section, then check J2. Note that this is grid line A and here is grid line H, and the reinforcements are expected to go from here, going straight up ahead and terminate at grid line A. While in the detail, we notice that the reinforcements terminate at grid line A based on this detail, where they must have terminated in grid line A. In layout, the reinforcement runs up to here and forms 90 degrees hook here, according to the detail, which is not in usual scenario. The reinforcement should have gone here because there is another beam here, this one. The reinforcement should have gone straight up to other end like this and have 90 degrees bend here. And we may ask, why is it so? It's because we did something wrong, and this usually happens during the modeling of a structure. If we review our model here, isolate this one, this first level. If we review our model here in this portion, unknowingly, we release the moment of this beam. And this is the primary cause of reinforcement layout inaccuracy. So even if we had imported the model for analysis and design, we could still run after these mistakes in RCDC and we have them corrected back here in staad software. These are the failed beams. We can highlight one of these beams and in the layout area, we can see the good connectivity between them. With this, rectification is easy to handle. In the design output, right click and click design. Then change to 400 by 600. And now it's okay. Then here, right click and change 400 by 600. Oops. Make it 450 by or 500 by 650. And now it's okay. One thing we have to see to it here that no column shall be smaller than beam framing in dimension in a particular direction. In a column beam joint, column flexural strength must be equal to or greater than that of beam according to NSCP section 418.7.3.2 or in ACI code section 18.7.3.2. So in this floor framing, how do we know visually that columns are stronger than beams? Here for example, it's clear that this column is wider than all of these beams here. Another thing to watch out is the intermediate beam. If we highlight this intermediate beam, again we can see the connectivity problem as we have discussed. We have two intermediate beams along this grid line and they must be in one group. However, they are not grouped together because of partial release of moments applied in this joint and in the other joint. It would be better to release the moment here if the beam is alone, just like this beam here. We can apply the partial release of moment in its joint connection. You know guys, many of staad users, whenever they see intermediate beams across the floor framing, they'll immediately think of release and partial release command. Do we think this primary beam will fail here if we make this connection fixed? Let us find it out. But before that, let's try to check the rebar detailing of these beams that we are right now talking about. Just highlight, and the group is G11. The reinforcements must traverse from grid line 10 to grid line 7. Now let's check the detail. Elevation and section, then grid line 11. And we can see the reinforcements in this detail. The reinforcement start from grid line 10 and terminate at grid line 9, only for one span. And we have two spans here. We will exit from here and do not save anything here for this time. We will go back to a staad file and we will do the rectification. After changes have been made in the Analysis and Design tab and in the toolbar, Click Run Analysis. After analysis has been run, we go to output and check any changes in base shear and do the scaling again, just like we did a while ago. And don't forget either to check the participation factor, for it is always at least 90% in both X and Y directions. If there are no noticeable changes, then proceed to RCDC again. When we remove the partial moment release in this location and in this location, including also here, all of them are highlighted, signifying that they are in the same group unlike before. And the fill beams here, if you can remember, in this location are now okay. These beams here, we need to resize, make this 400 by 650. And now it's okay. And the intermediate beams here are just fine. And if we check the rebar detailing, the group is G9. So let's go to reports, elevation and section, then G9. See, rebars are now different from previous layout, and the primary beam is still the same as before, making this joint fix has no adverse effect to this beam. Well, it's not always the case. Counter-checking is important. Now we go to next level, but it won't work until we update the current status of staad file. So the current changes that we made here in RCDC will be transmitted to a staad file. To do this, go to File, and click Update Analysis. Click OK, and then exit this file will reopen the staad file. In opening staad file, we will notice another file here. This is the previous version and this is the updated version. We can erase this old version by clicking and pressing the delete key on our keyboard. And this new file, rename and remove extension name. That's it. Then double click it to open. Then run the analysis. After checking B shears, we now open again RCDC and proceed to next level. But it is always better to revisit the previous level every time staad file is updated, for whatever changes made upstairs might affect downstairs. And so everything is fine in this level. So we now proceed to next level. Go to file, then new, then no, then here 7.5. Okay, there's no problem here. Okay, everything is fine, there's no problem in this level. So let's go to next level again. Level 11. Oops, there are failed beams in this level. This is our group G22. Let us go to design input tab to know which location. So here, this is the location of failure beams. Here in grid line, let's go to reports. In the drop down menu, click failure diagnostics. So these are the failure type, TC max, and shear detailing. This shear detailing can be sorted out by increasing the depth, or sometimes both width and depth, or sometimes width alone. TC max can be solved by increasing the size. However, if changing size is not possible like this, if we check formula of shear induced where two columns and a beam are involved within a span in ECI code section 18.6.5.1, where BE is the earthquake induced shear force at the face of the column here, we can take a look at the shear diagram in the figure R 18.6.5 of this ECI code. This is MPR1 and this is MPR2. BE is equal to MPR1 plus MPR2 divided by Ln plus minus WLN over 2. In this formula, the lesser the span length Ln, the greater the shear. If we have these three columns interconnected with beams as shown here, the shear of this particular beam in this joint induced during the earthquake event is equal to BE, where BE is equal to MPR1 plus MPR2 divided by Ln plus or minus WU times Ln over 2. So in our floor framing, we have two options here to remove the TC max failure. First, we can remove either MPR1 or MPR2. So the shear force will lessen, meaning option 1 is to remove the column here, so this beam will now act as a cantilever. Option 2 is to remove the other column, so this length Ln will increase, meaning increasing the span will reduce the shear force. For me, I shall remove this column to make the beam act as cantilever. That's it. So back to our staad file, we'll execute this modification. So in this module, we are going to remove this whole column from bottom to top, and then run analysis, and again check the base shear. This column, here, 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 and then press delete on the keyboard. Now run analysis. Okay, let's check the base shear. For ALF, we have here 1753.93 along X direction. For J direction, we have 1934.71 kilonewton. Now for response spectrum, along X we have 1755.62. And for J direction, we have 1934.33. So everything is fine, there's no problem. And for the participation factor, 95, both X and Z direction. Let's go to level 11. So there is no more problem. The field beams due to TC max and shear detailing here are now solved by only removing this column.